Okay, greetings and welcome back to the second part of our discussion of collective coordinates in the context of these mass spring systems. I don't really know how to say this politely. I mean, at the end of the day, this is kind of messy, and I puzzle over what to do in cases like this, and I always have. I'm not sure. I don't know the answer. Whether a long calculation done in a detailed step by step fashion from start to finish that takes 40 minutes, whether that's a good use of people's time or not a good use of time. I think that in general, for me as a listener to other people's talks that and courses, that I think my preference is that they give me the conceptual underpinnings and then I accept the fact that I've got to go and do the work for myself. So that's kind of where I'm coming from, I think. So just as a reminder, we are in the process of four ways of examining the collective coordinate problem. The first way was to solve it as a mechanics problem and to solve the differential equations by scratch and sniff, by adding and subtracting the two equations. That was very specific to this particular scenario. The second way of doing it was uh, to use the idea of the stiffness matrix, is the way I could describe it. And that led us to an eigenvalue problem. And there I didn't really do the hard work, meaning, I suggested a solution of the form e to x1 naught, e to the omega t, and x2 naught, e to the omega t. We substituted those in, and we saw that, as with many of the great uses of mathematics, that we turn one problem into another problem. We turned a problem in coupled differential equations into a problem in linear algebraic equations. That's pretty awesome. And to solve those linear equations, probably the best place that I know for people to watch is some of the early lectures in Gilbert Strang's MIT online linear algebra things. He has a very beautiful way of seeing these things. Instead of doing the row representation, he does what he calls the column representation, and the determinant equals zero condition. You can see that as being a statement about linear independence and linear dependence of vectors. So the determinant zero thing just drops out completely naturally. And in the book that I'm doing with Ernan, we have that there. And again, if somebody wants to see it, I can send you the relevant notes. But I at the end of the day, we got the same solution. In other words, by solving the mechanics problem, we found x1 of t, x2 of t. These are the x1 of t and x2 of t that I write here. It's a mess, but that's the answer. And you tell me your initial conditions, and I can plot a time series like shown here. Now what I said is, okay, instead of that, let me try to trick us in the sort of fun sense where we know what we've put in. We've put in this continuous set of trajectories, but now what we do is we sample it at equally spaced intervals, and I didn't have to do that. I could have spaced it at non-equal time intervals, and I get a series of points. And the question now is, what do I do with that data? This is a little bit of a weird way to use the word data, but I have these points. It's a time series, and now I want to figure out what to do with it. This led me to what I think is this very important idea of summary statistics. And what I'm claiming is that if I have a single variable, then the moments of my probability distribution are the summary statistics. And, I've been a fan of up to the fourth moment. I like the fourth moment because it tells you about whether or not there's a trough in the middle of a distribution, mu4. But for our purposes, usually we use mu1 and mu2. Now, the question is, how do I generalize that if I have more than one variable? And the answer is the covariance matrix. But it's very important to know the covariance matrix is a summary statistic. It's a way of characterizing this high dimensional probability distribution. In other words, I've got P of x1 and P of x2. And if I have a transcriptome, then I got P of gene 1, gene 2, G3, gene 4, blah, 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 blah. There's some probability distribution of that whole big mess. And the covariance matrix is a scheme for us to arrive at a summary statistic. So that's where we were at the end of last time. At the end, I saw that it was already 30 minutes. That was too long. I apologize to those of you that like to watch these things in 15-minute snippets, as I do. I mean, I don't sit and watch my own, but I watch lots of other people's short videos. I find that to be fantastic. I love the iBio seminars videos. Some of the KITP videos are fantastic, and I can go on with that. Many, many things in mathematics. For example, Professor Maynard, one of the guys who has won the Fields Medal, has some cool things on analytic number theory that I like watching. But I definitely prefer the vignette format. Maybe that's a loss of attention span. I don't really know. So where are we? What I'm going to do now is something that I feel a little sheepish about. I'm not that excited about it, but I am going to resort to trying to walk you through this analysis by showing you the results as tourism. And what I recommend is that if you want, that you can take screenshots, and even for the students that are in my current course, I suspect that I will not have them do this, although I think it's beautiful and super interesting, and can't tell you how much fun that Hernan Garcia and I have had going through this together. I mean, we've probably spent a year on it, on and off. So back to the key points. Here is the covariance matrix. Now, I'm going to show you two ways to go after this. Method number one is we're going to take the analytic solutions for x1 and x2, and that will permit us to compute the elements of the covariance matrix analytically, and that's cool. The second way we're going to do it is we're going to compute the elements of the covariance matrix by sampling these time series. In other words, I can just basically take the data as data points, and I can compute what x1 average is. You can kind of already see it by eye. It looks like x1 average is maybe about 0, and you can do that, and then given that data, we can compute a numerical value of the covariance matrix, and we can go from there to perform the things that we're about to perform. Okay, so what is the idea here? So if I want to find average of x1, notice above that I require average x1 in order to compute the covariance matrix. What that amounts to is that I've got to take this original thing, and I need to average this. So this whole thing was x1, and now I need to average it. And when I say average it, I mean evaluate this integral. And what we're going to find is that essentially all of these guys, all these independent sines, cosines, etc., they're all 0. So the average value, average x1, average x2 are 0, end of story. The next thing is that we want to calculate the second moments. And to do that, that requires us to evaluate integrals like this. And here you can see that we used a trigonometric identity. So I want to find the average of sine omega s, cosine omega a. I use the trigonometric identity to arrive at this. We do our integrals, and once again, we get zeros. So that's fine. But now, then there are also terms of this variety, cosine squared omega t, and those are actually non-zero. Again, you need to take a screenshot, but here's the idea. We use the fact that cosine squared of x is equal to 1/2 1 plus cosine 2x. We use that identity, plug it in. We know how to do the integral of cosine. We know how to do the integral of 1. We end up with this result. This term cancels out, and we're left with a half. So that's cool. We can basically, as a result of this, we can compute these big, messy correlation functions. And I agree that the expressions look daunting, but I just remind you that this big mess is what we just spent all that time in the previous vignette on. It's basically saying that I can write the position of the two masses as a superposition of my symmetric and my anti-symmetric modes. That means there's a total of 4 constants that respect the initial conditions. The initial condition is the x1 initial position, the x2 initial position, x1 initial velocity, x2 initial velocity. Those are the parameters that are featured in this big giant expression. And now I have to compute the average. That means I need to evaluate these various integrals. And there's the result. So I give you this as an exercise. Again, you can take a screenshot, or you can just come back to the video and take a look at it. But everything you need to work that out is a matter of doing some integrals. And similarly, we can work out these guys. which is the off-diagonal terms, and those also can be resolved analytically. And here's that result. So very interesting. So bottom line is that what I'm saying is that the covariance matrix, which I'm gonna use shorthand here: x1 squared, x1 x2, x1 x2, x2 squared. We actually are able to figure these things out. We can figure them out by plugging in our understanding of what the trajectories were, which was right here. So that's x1 of t. So I plug that in, I turn the crank, and when all the dust settles, the covariance matrix has this extremely simple form where alpha and beta are parameters that depend on all this stuff that you see right here. In other words, that is beta. That big mess is beta. And what does it depend on? It depends on the initial conditions through all of these things, so the initial positions, and it depends on the frequencies. The frequencies, the antisymmetric and the symmetric modes. So I can diagonalize this matrix. That corresponds to these eigenvalues. And that's interesting. And I also can compute the corresponding eigenvectors, and lo and behold, we get the same eigenvectors out that we got earlier. What do I mean by the same eigenvectors? Remember, the symmetric mode was 1, 1, and the antisymmetric mode was 1, minus 1 in the language of these vectors. So I'm ready now to just come back to this again. So what I've told you is, so what I've told you is that out of this analysis, we're able to deduce the natural coordinates of the system by just looking at the data, if you will. Okay. So so I've talked about this problem 3 ways now, and now I'm going to talk about it the 4th way, which is the data analysis way. So the data analysis way means we go back to the set of data points and we perform the operation. The operation, again, was we want to find covariance matrix, and in my loose notation, it's going to be written like this. Okay, I've been a little bit sloppy, but earlier I wasn't. So that's what I want to compute. And to do that, we can take each data point. So in other words, when I'm asked to find x1 average, what does that mean? It means I sum over all the data points, n equals 1 to capital N data points, x1. That's how I find the average value of x. And if I want to find x1 minus x1 averaged, then I've got to take the difference. I've got to subtract off the average and to sum them up 1 by 1 by 1 by 1, each data point. And if you do that for the data that I showed you earlier, that's the covariance matrix. And what we find is that the eigenvectors that emerge are these. That has to do with some imperfections, if you like, about the finite data set. And interestingly, the last thing I would say, and this is another exercise for you as the listener, is that you can do this exercise. In other words, you can actually perform a rotation of coordinates by hand. So let's say we decide to rotate our coordinate system by an angle alpha. And in this new coordinate system, we compute the covariance matrix in that new coordinate system. So that is to say, we do a transformation of coordinates, and then we compute the covariance matrix. And what we're plotting here is the elements of the covariance matrix as a function of that rotation angle. So check it out. And what we see is that at 45 degrees here, that the off-diagonal term, which is that one, vanishes. That is to say that by rotating the coordinate system, we've separated the variability in our data into 2 independent pieces. Okay, so this was all a interlude, as you can see at the top of the screen. This is an interlude on finding the right coordinates, and what it is it's in anticipation of the 2 biological exercises that we're going to do now. We're going to do two seemingly extremely distinct case studies. The first one will be to look at transcriptomes. So the cell is a bag of RNA. And what we will do is we will synthesize numerically a data set in which we put in, using the tools we've already learned about gene expression, we create a transcriptome for 1,000 cells or 3,000 cells or whatever. And then we bring the tools that I've just described to bear on that, for example, using the covariance matrix and so on. And the second example will be a really interesting case study done by this guy Stevens, who's in Holland, and which I can't remember whether he calls it the eigenworm or we call it the eigenworm. I don't remember anymore, but it's a really, really interesting decomposition of the motion of the worm. And then I will also point you to several beautiful studies by Julie Theriault in which she looked at several problems in cell shape, one for, if I remember correctly, Colobacter, and the other for keratocytes, I think, in which she studied in the case of keratocytes, she studied their motion, looked at the size and the shape of the cells, and tried to find out whether the data forced her to, through this principal component analysis idea that we're talking about, to identify what are the key variables that dictate the motion. Another way of saying this is that if I told her, or she told me, hey, yeah, I know the aspect ratio, I know the size, or I know the degree to which the cell is bowed, if I have that information, then I actually can say something a priori about the rate at which it moves and the directionality and so on. So those are the kinds of things that we're going to do with this methodology. I hope that you take the challenge and you work through some of the math that I've shown here, and I look forward to doing those next examples.